Hello there, welcome to this video. In this video, we are trying to learn how to draw the free body diagram for the truss structures. As we know, these truss members mostly using for the construction of the bridges. That's maybe to the railway bridges or maybe the road bridges. So then in this case, why we need to draw the free body diagram? We need to find out what is the reaction forces are generating at the supports. At the same time, what are the internal forces are going to be developing due to the carrying the load. As we know that these truss members, mostly they will take the two types of loads. The first one is going to be the tensile load, second one is going to be the compression load. In these consequences, the members are going to be either maybe elongate or maybe the contraction. It means the load is exactly acting at the joints of the members. The load cannot act at the middle of the member. I hope you are able to understand what is the main function of the truss and exactly where we have to apply the load. So in this diagram I have taken, there is three truss members, 1, 2 and 3. At the same time I made it to join here at A, at B as well as at C. And similarly there is a triangle support I have taken, and here is the hinge support I had given at the joint. And similarly the external force is acting at F, the external force F at C. So there we can see we need to draw the free body diagram to find out the sum of the unknown parameters, just like the reaction forces at A, B and internal forces in this member 1, 2 as well as the 3. These two things we need to be calculated. So in this case, the first I am going to be taking the reactions at A as well as the B. For this one, the free body diagram I am taking. So there we can see the free body diagram I am going to be, that means the total structure of the truss I have taken, and then I am removing, as we know the free body diagram, we first remove all the supports and show with the reaction forces. At A, I remove this one, we have to assume that the member is going to be trying to move in the downward direction. So the reaction force at joint A, it is going to be generating upward direction. And similarly at B also I removed, then reaction force is coming, here is the RB. There we can see that is at the joint B. And similarly the external force is going to be coming over here, that is the F at C. There we can see, and I want to find out the reaction forces at A as well as at B. So then what equations will help? That is going to be equations of equilibrium will going to be helpful. So that's going to be sigma f of x equal to 0. So in this case, can you see there is no horizontal forces in this member. So then this equilibrium equation is not required for us. But now what equation it will helpful? That is the sigma f of y is equal to 0. That means algebraic sum of the forces acting in the vertical directions are equal to 0 on this member. So that I am going to be taking over here, that is equal to. So in this case we need to be identify the positive as well as the negative sign convention. Upward direction I am going to be considering the positive, the downward direction I can take the negative. Vice versa also we can assume. So in this case what will happen? The two forces are acting in the upward direction and one force is going to be acting in the downward. So that I am going to be taking RA plus RB is equal to F. This is the equation 1 I have taken. So in this equation RA as well as the RB is the two unknowns. It is very difficult to calculate. This will become statistically indeterminate structure. So for this one I am going to be taking the moments. So that's going to be here. So that's going to be the moments with respect to A is equal to 0. There we can see when I am going to be taking the moments at A, so the moment is nothing but force into perpendicular distance. So that's going to be force into perpendicular distance. If I am going to say the force is there but there is no perpendicular distance, automatically that's the moments because of at A is going to be 0. But RB is acting certain distance, that is the perpendicular distance, AB distance is there, and similarly when I am going to be taking the line of action of the force, it is going to be intersecting, that I am going to say the D. That means the line of action of this force is acting at a distance of AD. So there we can see here, so the same moments I am going to be taking here. At the same time sign conventions I am going to be taking, this is going to be clockwise is the positive and anti-clockwise is going to be the negative. So then I am going to be taking, can you see the line of action is moving in the clockwise direction, right? And this RB is moving in the anti-clockwise direction. So when I am going to be taking the line of action, that we can see. So in this case what will happen, already we told, anti-clockwise that is going to be RB into perpendicular distance, that is the AB. That is equal to, because this is moving in the clockwise direction. I took the negative. That's going to be F into AD, I can take it. So then RB is equal to F into AD by AB distance. These are the perpendicular distance. Now by using this equation, I can calculate your RB. Once if I am calculating RB, then I am going to be substituting in the equation 1 so that I can calculate your RA also. So from this total free body diagram, I have found here RA as well as the RB, that as the reactions. Now we need to find out the internal forces in these members. So to find out the internal forces, we need to take the free body diagrams at different positions. There we can see there is a joints at A, the B as well as the C. In the previous free body diagram, we have evaluated A magnitude as well as the B magnitude. Once we know that, now I want to draw the free body diagram at A, because if you want to take the free body diagram for the joint, we must know at least one force at that joint, so that your calculations are going to be very easy. Either you can take at C or B or A, because now we know the three forces in this structure, so that we can calculate easily. So then I am going to be taking at A, so that is going to be the point A. Now we know the reaction force is coming in the upward direction, that is the RA. And similarly, I want to find out, as we know, this is the external force is going to be coming. The internal forces are already existed in this member because they are transmitting the force from this point C to the point A as well as the D. Now, I want to convert the internal forces into external forces. So, my process is that I am going to be cut the member 1 as well as the member 2. So that I can convert the internal forces into the external forces, then I can calculate those forces here. There we can see that one force is going to be acting in this direction, that is the internal force. There we can see this reaction force is moving in the upward direction. So then your reaction force in this member is trying to lift in the upward direction. So then automatically what will happen, this means member is going to be subjected to the compressive forces. But internally there is a tensile forces are going to be generating. So that's going to be your F1 I am going to be saying. And similarly, the member 2 is going to be subjected to, that means it is moving in the upward direction. So that means it is shifting from this position. That means this member is going to be subjected to the tensile forces from the externally. But internally, there is a compressive force is going to be generating. Suppose this is my assumptions I am going to be taking, right? There is no rule is that F1 is acting exactly. But that assumption has some scientific explanation, is that when it is moving upward and downward direction, then this member, what type of stresses are going to be generating? Either it is elongating or contracting. Okay. So from this one, it is making an angle of the theta 1, right? So now what I am going to do, so the two forces are there, RA and F1, one is in the horizontal direction and R2 is going to, F2 is in the horizontal direction respectively. But F1 is making an angle theta 1 with respect to the horizontal axis. So that we need to be resolve it. So how I am going to be resolving? One is going to be opposite direction. That means the vertical component is going to be over here and this is going to be the horizontal component, right? So that I am going to be taking here by using the equations of equilibrium. That's going to be sigma f of x equal to 0. So from this equation, what I am going to writing? So this F1 resolved into the horizontal. That means this force I am going to be resolved into the horizontal, but it is acting in this direction. So this is going to be your F1 opposites, that means adjacent side is going to be cos theta 1 and one force is going to be acting in the vertically downward direction. So that's going to be your F1 sin theta 1. So that I am going to be removing your force of the F1. Can you see the F1 I have resolved into the two components, one is the horizontal, one is the vertical, and I assume this one is in this direction. So this is also vertical. So the two forces are there in horizontal direction. So that's going to be F1 cos theta 1, right, plus F2 is equal to 0. There we can see this is the third equation we are going to say. F1 cos theta 1, F2 are in the same direction, that I got the positive, right? So similarly, I am going to be taking sigma f of y is equal to 0. So in this equation, only the two forces are going to be coming. Only the two forces are coming, that's going to be RA F1 cos theta. So that upward direction is going to be the negative, downward direction is the positive, whatever you can take it, that's going to be F1 sin theta 1 is equal to RA. From this fourth equation, I can find out the F1. Once if I am going to be calculating the F1, then I will substitute in the third equation, then I can calculate the F2 also. So this way we are going to be calculating the F1 as well as the F2 in their respective members after we cut it. Similarly, we are going to be find out the internal forces in this member BC, that means the third member. I am going to be taking the free body diagram at B. So there we can see, so this is going to be your RB force acting vertically upward direction, and this force is going to be acting in this direction, that is the F2 already we have seen in the last free body diagram. And similarly, this member is going to be subjected in this direction, that is the F3, and it is making an angle theta 2. So similarly, this F2 I am going to be resolving into the horizontal and vertical. So directly I am going to be taking f of x equal to 0. So that means one force is going to be acting in this direction, that means horizontal component of F3 is going to be F3, adjacent side is going to be cos theta 2. And similarly, this force is going to be F3 sin theta 2, because this is going to be your vertical component. So now F2 plus F3 cos theta 2 is equal to 0. Already we know the F2 value, so that we can calculate from this one is the F3. So this way we are going to be calculating. Suppose you are going to be taking sigma f of y is equal to 0, that's going to be F3 sin theta 2 is equal to RB. From this equation also we can calculate the F3 value. So when it is possible, when we know the angle of this theta 1 or geometry of these members, that means in terms of the length of the members, if you know, we can calculate easily. So I hope you are able to understand how to draw the free body diagram and how to calculate the unknown forces like reaction forces as well as the forces in these members. So still, if you feel any confusion, please put in the comment section so that I can reach out to you. Thank you.